Hello students, in continuation with our quick recap series, today we'll take up electric flux and Gauss theorem. In our previous discussion, we have done electric charges and Coulomb's law. After that, we have done electric field and potential. And in continuation with that, today we are taking electric flux and Gauss theorem. In today's discussion, we'll take electric lines of force, properties of electric lines of forces, electric flux, types of electric flux, Gauss theorem, application of Gauss theorem to point charge, linear charge distribution, planar charge distribution, charged spherical shell, and spherical charge distribution. We'll also take some conceptual type questions and numericals based on the topic discussed today. Electric lines of forces. Electric lines of forces are the imaginary lines. Tangent to them at any point gives the direction of electric field at that point. So this is the first definition which we can take for electric lines of forces. Suppose this is the electric lines of force. So if I take any particular point and if I draw a tangent at that point, this tangent will give the direction of electric field at that particular point. There is another definition. It is the path followed by unit positive test charge if it is free to move. If it is asked to define electric lines of forces, prefer to give the first definition. Second one will help you in visualizing many properties of electric lines of forces. So you can remember this one also. Let's now take properties of electric lines of forces. We'll take these properties one by one. So first one is electric lines of forces originate from positive charge and terminate on negative charge. Suppose this is the point where we have a point charge plus capital Q. It is a positive charge here. So the electric lines of forces are originating from it. So you can see that we have shown electric lines of forces coming out from this. Whereas if it is a negative charge, like here I am taking a negative charge there, minus Q. And now you can see the electric lines of forces are terminating on it. So they are coming to this particular charge and they are terminating. We have also taken one more way to define electric lines of forces as the path followed by unit positive test charge if it is free to move. So if I take for the first one, you have the charge plus Q at this point. That means you have a positive charge here. Imagine you have a test charge plus delta Q at this point. So what will be the path followed by this? This charge will experience a repulsive force. As a result, it will move away from it. So this one will give the path followed by unit positive test charge, which we have kept at this particular point and it is free to move. So this will give the electric lines of force for this charge. Similarly, if the test charge is here, again, it will experience repulsive force due to this one. So it will move away from it. Wherever we have put the charge in the vicinity of the positive charge, it will experience repulsive force, so it will be moving away from. Whereas for the second case, if I take test charge plus delta Q, and if it is here in the vicinity of the negative charge, it will get attracted by this and it will move towards the charge. If it is kept here, again, it will move in this direction towards the charge. So they will terminate on the negative charge. No two electric lines of force can ever intersect each other. If I have one electric lines of force here and this is the second one, we say that they will never intersect. Now, why they will not intersect? Because we have said that at any point to the electric lines of force, if I draw a tangent, it will give the direction of electric field at that particular point. If it is intersecting, then corresponding to the first one, suppose this is the first electric lines of force, so I can draw a tangent in this direction. Similarly, for this particular line, that is the second one, again, there can be a tangent drawn here. So at the same point P, now you have two directions of the electric field, which is not possible. Because if I take tangent to electric lines of force at any point, that gives the direction of net electric field at that. Due to the different sources, the electric field at a particular point may be in different direction. But if I take one particular point the net value of electric field at that point will always be. This is why we say that two electric lines of forces can never intersect. Because if they intersect, in that case, there will be two directions of electric field at the same point corresponding to the two electric lines of force which we have taken. So, which is not possible. Electric lines of forces do not form closed loop. If I take that we have the electric lines of force and it is forming a closed loop. If it is forming a closed loop, it means if I take any particular point, suppose here, in that case, electric lines of forces, suppose if it is like this, closed loop it is forming. So here it is originating at the same time from this side, if I consider it is terminating also. So that means at the same point P, it is originating from that point as well as it is terminating. We have said that electric lines of forces originate from positive charge and terminate on negative. It simply means at this particular point, you have positive as well as negative charge simultaneously. At same point, you cannot have positive and negative charge simultaneously. At that particular point, there will be some net value of the charge. It may be either positive or negative. So, obviously, in that case, it is not possible that they will be forming closed loop. Electric lines of forces are the continuous curve. Here, if you have the electric lines of forces, they will not show any breakage in their path. Like if it is there, it will not show here breakage. Because if it is showing breakage there, it means electric lines of forces are disappearing at this particular point, and again it is appearing from this point. This will violate law of conservation of charge, where we say that charge can neither be created nor be destroyed. So if I take, say, unit positive test charge, and we take at this particular point, if the charge is disappearing, it means the charges has vanished or it has been destroyed. So again, at this particular point, second point, if I consider that electric lines of forces is originating from that particular point, it means there is positive charge developed at that point, or it has appeared. So it will violate your law of conservation of charge. That is why we can say that electric lines of forces will not show any breakage in their path. It will always be a continuous curve. That number of electric lines of forces per unit area of cross section about a point is proportional to magnitude of the electric field at that point, or strength of the electric field at that. Suppose if I take one point here, and if I take any cross-sectional area, then number of electric lines of forces per unit area about this particular point will give you the strength of the electric field at that point. Here, if I consider at this one, same area of cross-section I am taking, but at this particular point, that is the second point. This is suppose your point 1 and this is your point 2. So electric field, if I consider in this particular case, as the number of lines of forces per unit area of cross section about 0.1 is more here as compared to the second one. So electric field at 1 will be more than electric field at 0.2. Electric lines of forces do not exist inside a conductor. Now, inside a conductor, the electric field is zero. No electric field exists inside a conductor. And how we have said for the electric lines of forces related with the electric field intensity, number of electric lines of forces per unit area of cross section about a point is proportional to the magnitude of the electric field at that point. So if electric field is zero, obviously electric lines of forces will also be zero there. So that is why we can say that electric lines of forces do not exist inside a conductor. Electric lines of forces meet a conducting surface normally. This is the conducting surface. And we have electric lines of forces meeting the conducting surface. So this is the direction of the electric lines of force, and it is meeting at this particular point. Now, if it is meeting at this point, in that case, what we can do, if I take a tangent, this is the tangent, it will give the direction of the electric field at this particular point, because we have drawn a tangent corresponding to this particular electric lines of force. So this will be the direction of the electric field. Imagine you have a charge Q at this particular point. If the charge Q is there, it will experience force, and the force will be in the direction of the electric field. So it is your Q into E. This is the force experienced by the charge Q. Now, this particular force I can resolve in two directions. Suppose this is at an angle theta, that means this particular angle is theta. So it will have the two components, one along the surface as your f sine theta, and other will be perpendicular to the surface as f cos theta. If you consider the component that is your f sine theta, this is the component of the force along the surface of the conductor. If it is along the surface of conductor, it means the charge will move in the direction of the force. So for this particular diagram which we have drawn, as it will be moving from left to right, it means the left hand side points will be at higher potential as compared to the point on right side. Any point on left side is at higher potential as compared to a point on the right side. But since you are taking a conductor, a conducting surface is always an equipotential. If it is equipotential, it means there will be no motion of the charge because the charge will move from high potential to low. If the potentials are same, in that case the charge will not. And if the charge is kept on the surface, it will not move if we consider that there is no force along the surface of the conductor. So for that particular case, if I take f sine theta, this should be 0, and this will be 0 if theta is 0, because f will be there. Charge will experience force because there will be electric field as the electric lines of forces are meeting there. So force will be there, but sine theta term should be 0 so that there is no component of the force along the surface of the conductor. And if theta is 0, it simply means this theta we have taken normal to the conducting surface. So it means the electric lines of forces will meet any conducting surface normal. That is why we say that electric lines of forces will meet a conducting surface normal. Next, electric flux. It is the number of electric lines of forces passing normally to a given surface. This will be given by electric flux we represent, suppose by phi. So it will be related with the electric field as E dot A. And here the vector area is A. Vector area will always act perpendicular to the surface which is given. And E is the electric field. Suppose it is inclined at an angle theta. So as we have taken the dot product, it will be given as your EA cos theta. So phi will be E dot A for uniform electric field. If the electric field is uniform, you will get this expression. But if the electric field is not uniform, so for non-uniform electric field, it will be given as your E dot dA. We take elementary area dA, and it is the dot product of E and dA, and will integrate for the entire surface there. So that is why we write it as your E dot dA integral. This will be the expression for non-uniform electric field. Now the types of electric flux. First one is the positive flux. Second, we take it as the negative flux, and third as zero flux. How we are getting these flux there, or different types of the flux? Because the electric flux we have taken as E dot A. If it is your E dot A, then it is written as your EA cos theta. Since this cos theta value will depend upon the angle there, whether it is acute, obtuse, or it is 90. So depending upon that, we have the different values of cos theta, whether it is positive, negative, or 0. So that way, we take the flux of 3 different types as positive flux, negative flux, and zero flux. Let's take positive flux. Here, if we consider that electric field is making an acute angle here with the vector area. So if theta is acute, then cos theta term will be positive, because for acute angle, cos theta is positive. So in that case, this electric flux will be positive. In fact, any electric lines of forces which are coming out of the surface, so they will be taken as the positive flux. If you have electric lines of forces coming out of the surface, then they are taken as positive flux. Negative flux. If the angle between the electric field and the vector area is obtuse, then cos theta will be negative. And if it is negative in that particular case, the flux will be negative. In fact, if the lines of forces are entering through a given surface, in that case, like here, you can see that lines of forces are going into the surface. So incoming flux, you can say that it will be negative flux. Now, zero flux. If theta is 90, that means the angle between the electric field and the vector area is 90. So we have taken theta as pi by 2. And in that case, cos theta will be equals to 0. And if it is 0, then the flux will be 0. So anywhere, if the electric lines of forces are grazing the surface, like they are grazing the surface, here they are just grazing the surface. In that case, the angle between the electric field and vector area will be 90. And in such situation, we can say that we have the zero flux. That means no electric lines of force will pass through this surface. They will be just grazing. It will not come out of the surface or enter into the surface. Gauss theorem. The net electric flux through a closed surface is 1 by epsilon naught times the net charge enclosed by the surface. If you consider any closed surface, and if it is enclosing, suppose the charge q, by Gauss theorem we get E dot ds integral over closed surface. This is your qi by epsilon naught, where qi net charge which is enclosed here. So that we take it qi. And remember, when we take this particular symbol, this is the symbol we use for integration over a closed figure. So as we are integrating over ds, which is a elementary surface, so integration here when we take, it will be over a closed surface. So this is your Gauss theorem. This one we take only for the charges which are inside a closed surface. If charges are lying outside, they will not contribute for the electric flux there. Like if I consider that we have a closed surface here, we have the charge q1 which is positive, minus q2 which is here, q3 is lying outside. So if this closed surface is S, in that case electric flux through S, this will be only given as your q1 minus q2 by epsilon naught. It is the net charge which we are taking, which is inside the closed surface. Suppose if I have the charge q4 also lying outside, this will also not contribute. But if suppose q5 is there, it is lying inside q5. So in that case, for the second part, it will be equals to your q1 minus q2 plus q5 by epsilon naught. That will be the net flux through this closed surface. Let's take a derivation of the Gauss theorem. We have taken a charge, suppose q, at the point O. So here, this charge is inside a closed surface. So this is the closed surface which we have shown here. And now we take one point P. Suppose point P is there on this particular surface, and ds represents an elementary area about the point P. So this ds vector is the elementary area about the point P. If electric field at the point P is vector E, and the point P is at a distance r, so obviously we can write electric field as q by 4 pi epsilon naught r square. This is the electric field at the point P. So if I want to find what is the electric flux through this elementary area ds vector, in that case it will be d phi. It is d phi, which is your E dot ds. And in that case, we can write this as E ds cos theta. For E, if I substitute, it is q by 4 pi epsilon naught r square. And it is your ds cos theta. Now, if I just put this ds cos theta by r square at one point, this ds into cos theta will give the normal elementary area about the point P. So this ds cos theta by r square is your d omega. This d omega, we take it as the elementary solid angle. So it is the elementary solid angle subtended at the point O here. If I now take total electric flux about this entire closed surface, so it is your E ds integral over the closed surface, which will be q by 4 pi epsilon naught, then integration over closed surface for d omega, and total solid angle about a point is your 4 pi. So it is your q by 4 pi epsilon naught into 4 pi, and that will give you the value as your q by epsilon. So q by epsilon naught is the net electric flux over the entire closed surface, which we take it as your E dot ds integral over the closed surface. So now what we have got, E dot ds over the closed surface, this is your q by epsilon. This is the proof of Gauss theorem. Of course, we could have done this derivation by taking a symmetrical surface there about the point charge, say q. We could have taken a spherical surface, I could have derived it that one. But that will be not a general derivation, it will be a special case. Remember that Gauss theorem is applicable for any shape of closed figure. So that is why whenever it is asked to derive Gauss theorem, you derive it for an arbitrary closed surface, not any specific one. Let's now take applications of Gauss theorem. First, we are taking to find electric field due to a point charge. I want to find electric field due to a point charge using Gauss theorem. We have already done electric field derivation for a point charge using Coulomb's law. Now here we are doing it by Gauss theorem. So for this, what we do, we take suppose a charge plus q at particular point O. I want to find its electric field at a distance r from it. So r is the distance from the charge where we want to find electric field. So what we'll do, we'll construct a spherical Gaussian surface. This Gaussian surface will have the radius r and its center will be at the point where the charge q is located. So we take this one, and now if I take Gauss theorem E dot ds integral over closed surface as qi by epsilon naught. So for this case now, it is your elementary area if I take ds vector. So it is your E ds cos 0, because the electric field and the vector area for this particular case will be in the same direction. So it is your cos 0. This is equal to q by epsilon naught, because q we have taken as the charge which is enclosed by the surface here. So it is your E into 4 pi r square, because the integration over the closed surface or a spherical surface, this is your 4 pi r square. So it is your q by epsilon naught, and E will be your q by 4 pi epsilon naught r square. This is the expression for the electric field due to a point charge. This we have also derived by using Coulomb's law. So you can see that we can get directly the value of the electric field of same value when we are applying Gauss theorem. Let's take another application to find electric field due to uniform linear charge distribution. This charge distribution of infinite length, and it is uniform. So lambda is the linear charge density for this charge distribution. And this one, for this case, we take a cylindrical Gaussian surface. So this is the cylindrical Gaussian surface of radius r, length L, length we have taken it as L, and this is having its axis coinciding with the charge distribution. And we take elementary area like dA vector on the curved surface. This is one elementary vector. Then for upper flat surface, vector area is A. For the lower one also, it is your A vector. So it is your vector A in this direction, vector A here. Electric field is your E, which we have shown in this case. Now, that means this cylinder we can consider that it will have the three surfaces, one curved surface and two flat surfaces, upper and lower one. So if I want to find electric flux, we'll have to take the lines of forces which is passing through these three surfaces there. So let's apply Gauss theorem for this particular case. So if you take Gauss theorem, it is your E dot ds integral over closed surface. This is your qi by epsilon naught. So for this one, you have E dot A. This is for the flux coming out, say, from upper flat surface. E dot A may be the flux coming out from the lower flat surface. And E dot dA dash as the flux. If I integrate it, then you will get the total flux which will come out from the curved surface. And then we'll have to take the net charge enclosed by this Gaussian surface. So this is your lambda into L. Lambda is the linear charge density, length we have taken as L. So it is lambda L, and this is divided by epsilon. Now, if you consider angle between E dot A, if you take angle between electric field E and vector area A, in that case, this one is 90. So as this particular angle is 90 here, so it is your EA cos pi by 2. Second one is also EA cos pi by 2. And the third one will give you EDA dash cos 0 integral. And this is your lambda L by epsilon naught. Now this term cos pi by 2, cos pi by 2, these will be 0. So what we get here, E into 2 pi RL. 2 pi RL will give you the curved surface area of the cylinder. So E into 2 pi RL is lambda into L, and that will give the electric field as lambda by 2 pi epsilon naught R. So this is the electric field due to uniform linear distribution of charge of infinite length. Let's now take electric field due to a uniform planar charge distribution. We are taking uniform planar distribution of charge. Again, this one will also extend up to infinity. These will extend up to infinity there. Clear? And we take, suppose that surface charge density is sigma. Sigma is the surface charge density for this charge distribution. Again, we'll take cylindrical Gaussian surface. So we have taken a cylindrical Gaussian surface. In this case, orientation is like if you have the plane, it is kept perpendicular to that. So E is the electric field, and now we take this as the flat surface. So vector area is A. For this one on the other side, again the flat surface, this has the area vector A. And for the curved surface, we take elementary section to have an area dA dash. So dA dash will be the vector area of this elementary section. Electric field is E. So again, if I consider Gauss theorem and we apply it for this case, what we'll get? E dot ds integral over closed surface is qi by epsilon naught. For first one, it is your E dot A. Second is again your E dot A. That is the other flat surface. Then it is your E dot dA dash integral. This is for the curved surface there. And this will be having the charge enclosed, which is sigma into A. Sigma we have taken as the surface charge density. So sigma into A will give you the charge enclosed by this Gaussian surface. And this divided by epsilon naught. Now first term, now it will be your EA cos 0 because angle is 0 here. Second is also EA cos 0. Third term, E dot dA dash. This will be E dA dash cos pi by 2 because the angle is 90 degree here. You can see 90 degree. So this is your sigma A by epsilon naught. And this time this term will be 0, and now it will be first term EA, second term EA. So it is your 2 times EA, which is equal to sigma A by epsilon naught, or E will be equals to sigma by 2 epsilon naught. This is the electric field due to uniform planar distribution of charge of infinite dimension. We take it of infinite dimensions so as to avoid the fringing effect that happens at the ends. Similarly, for the linear charge distribution also, again we have taken that of infinite length. For that case also, to avoid the fringing effect happening at the ends. Now we are taking a uniformly charged conducting sheet and we want to find electric field due to this. So for this, again we have a conducting sheet. This time what we have done, we have kept the orientation normal so that you can see that the charges appearing on this surface as well as this surface as well as the charge on the other surface there. So these are the charges. Suppose I have assumed that surface charge density is sigma. We'll again take cylindrical Gaussian surface the same way as we have done for the planar distribution of charge earlier. So this time again, if you consider, you will have here E dot ds vector integral over the closed surface qi by epsilon naught. So it is your E dot A E dot A as the second term, E dot dA dash. And now this time the change here will be amount of the charge enclosed by the closed surface. So since it will have the charges appearing on both surfaces, sigma into A is the charge enclosed by this cylindrical Gaussian surface on one side. Similarly, on the other side, again, you will have the same amount of charge. So it will be your 2 times sigma into A. So it is the same way. Now you will get 2 times EA as 2 sigma A by epsilon naught. And that will give the electric field as sigma by epsilon naught. This time for uniformly charged plane conducting sheet, the electric field will be sigma by epsilon naught. Whereas planar distribution of the charge, which we have taken, it was your sigma by 2 epsilon naught. Let's now take to find electric field due to uniformly charged spherical shell. For finding this, suppose we have taken, this is the spherical shell of radius r and charge on it is capital Q. We want to find electric field due to this one at a distance small r. So for this, we'll take a concentric spherical Gaussian surface of radius small r. And this is suppose the bigger one, that is what we have shown that it has a radius small r there. So if I apply Gauss theorem here, E dot ds equals to Qi by epsilon naught, and this is your E dot ds can be written as your E ds cos 0 here, because the angle between electric field and the vector area if I take, so that will be 0. So it is your Q by epsilon naught. Now if I take first case, that when r is greater than capital R, radius of the Gaussian surface is more than the radius of the spherical shell. So for that it is your E into 4 pi r square, that is Q by epsilon naught, and this is your E equals to capital Q by 4 pi epsilon naught r square. Or if you take the second case, when small r is equal to capital R, so in that case it is your E into 4 pi r square, that will be Q by epsilon naught, and this is your E equals to Q by 4 pi epsilon naught capital R square. Capital R we have taken as radius of the spherical shell. One thing you can remember in this one, that if the point is lying outside the spherical shell or it is on its surface, we can treat as if whatever charges were there on the spherical shell, they are concentrated at the center. So they are there at the center, and we can take the electric field there. Treating that charge as a point charge, we can find electric field. So it is the expression there. When small r is less than capital R. Now this time what we have done, we have taken the Gaussian surface to have radius less than the radius of the spherical shell. So capital R was the radius, and here we have taken the Gaussian surface in this particular part. So now if I again apply Gauss theorem here, so it is E into 4 pi r square. Now we see that whatever charge were there, they were lying on the surface of the spherical shell. Or if it is your spherical conductor, then also the charge will lie only on its outer surface, not inside it. So in this particular case, here again, you have no charge inside this Gaussian surface. So the charge enclosed is 0, and that is why electric field there value will be equal to 0. If I plot a graph for this one, that is the graph between electric field and the distance. So up to capital R, that is the radius of the spherical shell, electric field is 0. So it is shown 0 here. And for the point which is lying outside, that means small r is greater than capital R. In that case, E will vary inversely to a square of the distance. So for that, it will vary like this. Whereas the electric field value, when distance is equal to r, that is on the surface of the spherical shell, it is your Q by 4 pi epsilon naught r square. That we want to find electric field due to uniformly charged spherical distribution, or it may be called as the spherical non-conducting charged body. So for that, if we take, charge will be distributed all over the volume of this. So suppose capital Q is the charge, it is distributed all over the volume of this spherical distribution, and we have taken its radius as capital R. Again, if you want to find electric field due to this at a distance small r, so for that we'll take a concentric spherical Gaussian surface of radius small r. So this will be the Gaussian surface which we have taken. So again, it is your E dot ds qi by epsilon naught, which is written as your E ds cos 0 equals to qi by epsilon naught. For first case, if I consider when r is greater than capital R, so it is E into 4 pi r square, that is your q by epsilon naught, or that will be equals to q by 4 pi epsilon naught r square. For second case, when we take small r is equals to capital R, that means the observation point is there on the surface of the spherical distribution. So it is your E into 4 pi capital R square, that is your q by epsilon naught, and that is again E is equals to q by 4 pi epsilon naught r square. If I suppose take the case when small r is less than capital R, so E into 4 pi r square, that is equals to 1 by epsilon naught. Now we'll have to take the charge inside this spherical Gaussian surface whose radius is the small r. So it is the charge per unit volume, which is your q by 4 by 3 pi capital R q, and this will multiply it by the volume of this small Gaussian surface. We'll take the volume of this small Gaussian surface, which is your 4 by 3 pi r q. So E will be equals to capital Q into small r divided by 4 pi epsilon naught capital R q. So we can see here that E is directly proportional to R. Alternatively, we can show this one as E into 4 pi r square equals to 1 by epsilon naught in terms of the volume charge density. Suppose rho is the volume charge density here. So this multiplied by the volume of the Gaussian surface, which is your 4 by 3 pi r cube. So in terms of the volume charge density, electric field here will be written as your rho into r divided by 3 epsilon naught. So this is the expression for electric field there for this spherical charge distribution when the observation point is inside. Let's take now the variation of E with R. So plot will be, it will be a straight line up to capital R, because electric field is varying directly to the distance. So E is directly proportional to R here, so it will be a straight line. And for outside point, when a small r is greater than capital R, it is E varying inversely to a square of the distance. So at the point R, that is on the surface of the spherical charge distribution, Q by 4 by epsilon naught r square will be the value of the electric field that we have shown here at this point. Let's now take some conceptual type questions. Let's take these questions one by one. So the first question is, what is the number of electric lines of forces coming out from 1 coulomb of charge in vacuum? So for this, suppose you have been given 1 coulomb of charge. We'll take a Gaussian surface around it. So it is a closed surface. So if I simply apply Gauss theorem, net flux will be equal to the charge enclosed divided by epsilon naught. Since the charge is your 1 coulomb, so in that case it is your 1 by epsilon naught. So this will be your 1 by 8.85 into 10 to the power minus 12. And that much will be your the flux. So it is your Newton per coulomb meter square. So that is the value of the electric flux, because you have taken 1 coulomb of charge in vacuum. A point charge capital Q is located at the center of a cube of side A. What is the electric flux passing through the cube? And second part, each face of the cube. So for this one, suppose we have taken the charge capital Q here, which is located at the center of this cube. This cube has the side A. The charge is at the center of this cube. It means the entire charge is inside a closed surface, that is the cube. So electric flux through the cube, if I consider, this will be equals to simply Q divided by epsilon naught. Second part, what is the flux through each face of the cube? Each face of the cube we are taking. Now, since the charge is at the center of this cube, so for the particular point center, all the 6 faces of the cube are identical. So in this case, whatever flux is coming out, it will go equally through all the 6 faces. So the flux through each face will be equals to 1/6 of the flux through the entire cube. So it is your 1/6 of Q by epsilon naught. A point charge capital Q is located at one of the corners of a cube of side A. What is the electric flux passing through the cube and through each face of the cube? Now for this particular case, here what we are taking? We are taking that we have a cube and the charge is now located at one of the corner of the cube. The charge which is at this particular corner of the cube is not completely inside the cube. So we cannot directly take it as the entire charge divided by epsilon naught as the flux passing through this cube. So what we do? We consider 3 more identical cube placed side by side. So here it is like this. This is the suppose second cube. This is the third cube. This is the fourth cube. And this particular charge which is here, now it will be at the center of one of the face, that is the bigger face of a cuboid there. And here dimension will be your 2a, and height is your a. But still, it is not completely inside. So what we do? We take another 4 cube lying above it. This is your 5th one, this is a 6th, this is your 7th one, and this is your 8th one. So now it is a big cube whose side will be equal to 2a. And where is the charge here? With respect to this big cube, it is at its center. So as it is at its center, so flux through this big cube. Now if you consider, the flux will be equal to simply capital Q by epsilon naught through this big cube. So, and this big cube is made of 8 identical small cubes. So the flux through each cube, this will be your 1/8 of this. So it is 1/8 of Q by epsilon naught. So that will be the expression. But you have to find the flux through each face of the cube also. So for that, what we do, the charge was there at one of the corner of this cube. And through this particular cube, the flux here through this cube is your 1/8 Q by epsilon naught. Now here you see that the electric flux or the electric lines of forces which are there, it will be grazing through these 3 faces. This is your one face, this is the another one, and this is the third one. That means the faces which are adjacent to this particular corner where the charge is located. So through these 3 faces, electric flux will be 0 because the electric flux or the electric lines of forces will be grazing through these surfaces. So they are not passing through it. So through these 3 faces, electric flux is 0. So now whatever flux was there, which is your 1/8 of Q by epsilon naught, whatever flux we have taken here, 1/8 Q by epsilon naught, this will pass through the remaining 3 faces. So this particular flux will pass through the remaining 3 faces. So through the remaining 3 faces, it will be equals to 1/3 of this one. So it is your Q by 8 epsilon naught. So that means it is your Q by 24 epsilon naught. That will be the flux through the remaining 3 faces which are not adjacent to this particular corner. Whereas the flux through the faces which is adjacent to this particular corner will be 0. An electric dipole of dipole moment P and length L is kept inside a spherical surface of radius capital R. What is the electric flux passing through the sphere? So suppose it is given that you have a spherical surface of radius capital R and it is enclosing an electric dipole of dipole moment P. Length is also suppose mentioned that it is your L. And you have to find what is the flux passing through this sphere. As it is an electric dipole, It means it is a system of two equal and opposite charges separated by a small distance. So for this particular sphere, this dipole, as it is lying inside, so the net charge will be 0. So in this case, flux will be 0. As the net charge enclosed inside this sphere is 0 because you have taken an electric dipole lying completely inside. A point charge capital Q is at a distance a by 2 from the center of a square plate of side A. What is the electric flux passing through the square plate? So we have to find what is the electric flux passing through the square plate here. So suppose here, this is the figure. You have this square plate of side A and the given charge is at a distance a by 2 from the center of this plate. So this is your Q. If you want to find electric flux through this particular square plate, we cannot take the electric field multiplied by area, although we can use it to find electric flux passing through it, but electric field value will be different at different points. So they will be at different points, so you cannot take directly just by putting the value of the electric field and multiplying it by the area of the plate. So what we do, we take identical plates enclosing this particular charge. So suppose this is your one face, that is another plate here. This is the second one. This will be the third one. Okay, the other side, it will be the fourth one, and this one that is on the bottom, it is your fifth one. So that means now these 6 faces of the plates are making a complete cube. And where is the charge located now? The charge is at the center of this particular cube of side A. So electric flux, if I want to find out through this particular cube, it will be equals to Q by epsilon naught through the cube. And now for the charge, which is at the center, all these 6 faces are identical. So the flux through square plate, this is your 1/6 Q by epsilon naught. So that will be the value of the electric flux. Which of the following correctly represents electric lines of forces through a spherical conductor? See, the first one, it is passing through the spherical conductor, second also, third one. Since electric field inside the conductor is 0 or no electric lines of force can exist inside the conductor, so on that basis, first, second and third electric lines of forces are not possible. So the only one which is shown that it is not lying inside, that is the fourth one, and also it is shown that it is meeting the conducting surface normally, because if you just join it, it will be passing through the center of this. So that means it is first not lying inside, secondly it is meeting the conducting surface normally. This is suppose the fifth one. Here it is not lying inside, but this is also not the correct one because it is not meeting the conducting surface normally. If I join it with the center, it is not striking it normally. So the fifth one is also not correct. Let's now take a few numericals. We'll take these numericals one by one. So the first one, consider two hollow concentric spheres S1 and S2 enclosing the charge 2Q and plus 4Q respectively as shown in the figure. Find out the ratio of the electric flux through them. How will the electric flux through the sphere S1 change if a medium of dielectric constant epsilon r is introduced in the space inside S1 in place of air? So if we have to find the ratio of the electric flux through them, so what we can do, electric flux through S1 and electric flux through S2. If I take the ratio, it is your 2Q by epsilon naught because it will be for the first sphere and for the second one. For second one, it is your 2Q plus 4Q because inside S2, these two charges are there. So it is your 2Q by 4Q divided by epsilon naught. So this is your 2 by 6. That means it is 1 by 3. So the required ratio is 1:3. In the second part, it is asked, how will the electric flux through the sphere S1 change if a medium of dielectric constant epsilon r is introduced in the space inside S1 in place of air? So in place of air, you are using dielectric medium of dielectric constant epsilon r. So for this case, suppose if I take phi s1 dash, this is your q, that is your 2q now, charge inside, divided by epsilon naught into epsilon r, because it will be the permittivity of the medium. An electric field in a region is given as E equals to 4 into 10 to the power 4 I cap Newton per Coulomb. Find the flux of this field through a square of 5 centimeter side whose plane is parallel to YZ plane. What would be the flux through the same square if the plane makes an angle 30 degree with the x-axis? Now for this one, if I consider that this is the square plate, it is lying in the YZ plane. So if it is lying in the YZ plane, it means vector area will be lying in the x-axis. So this will be the direction of the electric field in the direction of the electric field here. So flux will be equals to E into A cos 0 degree. So this is your 4 into 10 to the power 4 into 5 into 10 to the power minus 2, as it is 5 centimeter. So this is your 4 into 10 to the power 4 into 25 into 10 to the power minus 4. So this is your 100 Newton per Coulomb meter square. So this will be the flux through this square plate. Now for the second part, it is given that the same square is turned so that its plane now makes an angle 30 degree with the x-axis. Remember, if the plane is making an angle of 30 degree here, this is 30 degree, it means the vector area will be making an angle of 60 degree with x-axis. That is the electric field direction, because electric field is in the x-axis direction. So for this particular case, it is now your EA cos 0. It was your EA cos 60 degree. So this is your, this we have already calculated. It is your 100. Now it is your cos 60, that is your half. So it is your 50 Newton per Coulomb meter square. That will. In a region of space, the electric field is in the x direction and it is given as E equals to E naught xi cap. Consider an imaginary cubical volume of age A with its edges parallel to the axis of coordinates. Find the charge inside this volume. So here, suppose this is the Q. We assume that its one plane, say this one, is at a distance x. Obviously, the other plane, if you consider, suppose this is the other plane. So this particular plane, if I consider, it is at a distance x plus a. Electric field on the first surface and second surface will be different because it depends upon the distance. So the flux, if I consider the net flux, if you take, so delta phi will be equals to E2 into vector area, because the angle here will be 0 degree. So it is your E2A square minus E1A square. And here E2 will be equals to E naught. What is this distance? This is your x plus a, because it is your E naught xi cap, and this multiplied by a square minus E naught x a square. So this is E naught a q, because x term will get cancelled and you will get E naught a q. This is the flux through this q. So if I find out the charge, delta phi will be equals to q by epsilon naught. So that means q will be equals to epsilon naught into delta phi, which is equals to E naught into a cube multiplied by epsilon naught. So this is your epsilon naught E naught a cube. This is the charge inside this volume. Flux through a surface of area 100 meter square lying in the xy plane, and the unit is your voltmeter. E is given as your I cap plus root 2 j cap plus root 3 k cap. Now here, as this particular surface is lying in the xy plane, it means the vector area will be along the z-axis. So vector area I can take that it will be equals to 100 k cap. So if it is asked what is the electric flux, so this is your E dot A, means it is your, this is your I cap plus root 2 j cap plus root 3 k cap dot 100 k cap. Now I dot k, j dot k will be 0, so it will be simply 100 root 3, which is your 173.2 units. That is the electric flux. Two charges of magnitude minus 2q and plus q are located at the points A0 and 4A0 respectively. What is the electric flux due to these charges through a sphere of radius 3a with its center at? For this, if you consider, this is suppose the sphere whose radius is given as your 3a, so that means this particular distance is your 3a. We have to find what is the flux passing through this sphere. And the charges where they are located, one is located here, that is minus 2q at a distance a from the origin, because its coordinate is given as your a0, and the second one is at a distance 4a. So the electric flux through this sphere, this is equals to qi by epsilon naught, net charge enclosed there by this surface. So net charge is only minus 2q because plus capital Q is lying outside. So it is your minus 2q by epsilon naught. So this will be the electric flux through this sphere whose side is 3a. So this was our discussion on electric flux and Gauss theorem. In our next discussion, we'll take electric dipole. We'll take the different topics of electric dipole, like what is electric dipole, what is electric dipole moment, what is the direction of the electric dipole moment. Also take electric field due to the dipole on the axial and equatorial line, force and torque on electric dipole if it is kept in uniform electric field, as well as what is the work done in rotating a dipole in uniform electric field, energy stored in an electric dipole in uniform electric field. So all these we'll discuss in our next discussion.